Hey guys, it's Miss Johnson and I'm here to bring you our third piece of section 3.2 in our book. Today we're talking about the role of the standard deviation of the residuals and also R squared, which is the variance of the residuals. We're talking about basically how well does this line that we've found fit our data. So far in this section, we've talked about a regression line. We've talked about finding the least squares regression line. We've talked about how to put those things on our scatter plot. And today we're going to talk about how good is the model that we've found. Here are those two slides of learning targets again. There are a lot of learning targets in this section like we've talked about before. Yep, there they all are. All right, so how well does the line fit our data? That is always a question because we know that data is messy. We know that data is not always pretty. So when we find this LSRL that goes through our data, how good of a model is it? How accurate is the model? And how smart is it for us to use that model to predict other values? Because if it's not a great model, then we don't want to use it to predict other values in our data set. So it says to assess how well the line fits all the data, we need to consider the residuals for each observation, not just one. So using these residuals, we can estimate the typical prediction error when using the LSRL. So what is our typical error? How off are we when we use this LSRL to make a prediction within our data range? One of the values that we're going to look at to determine how well our line fits our data is the S, the standard deviation of the residuals. The standard deviation of the residuals measures the size of the typical residual. So just like standard deviation in a normal distribution set measured the typical distance away from the mean, standard deviation of residuals measures the typical residual away from the LSRL. So what is our typical distance away from that least squares regression line for each of our data points? That's what S is. It says that S is measuring the typical distance between the values, the actual values of Y, and the predicted values of Y. The other thing that we are going to look at today is the coefficient of determination. So we have an R squared there. It says the standard deviation of the residuals gives us a numerical estimate of the average size of our prediction errors. There is another numerical quality or quantity that tells us how well the LSRL predicts our values in the response of Y, of the response variable Y. The coefficient of determination, so that's R squared. We talked a lot about R back in section 3.1. R was that correlation coefficient. R squared is literally the square of R. That's it. It's R and R squared. R squared is the square of R, and we call that the coefficient of determination. So R squared is it's a pretty tricky number to understand, to wrap your head around. The cool thing about it being the square of R is one thing we know about R must be between -1 and 1, right? So we know that a perfectly negative correlation has a -1 R coefficient. A perfectly positive association or correlation has a +1 R coefficient. So if you take any value between -1 and 1 and you square it, your R squared is going to be from 0 to 1. Okay, so it's going to be some decimal between 0 and 1 because obviously we all know that if you square the negative values over here on the left-hand side, a negative times a negative gives us a positive. -1 times -1 is +1. +1 times +1 is +1. So we're between 0 and 1. That's what leads us into the fact that R squared is actually a percent. So R squared comes from squaring R. And because that puts us between 0 and 1, we can talk about it in terms of percent. So the R squared value is a percent. What it's measuring is it's measuring the amount of variability in the response variable that is accounted for by the LSRL. So our LSRL is going to create variability when we use it to make predictions. When we make predictions in our data range, Like if I go back to the Ford F-150 and my data range for the Ford F-150 example was from 0 miles up to 160,000 miles, and then we used that LSRL to predict 100,000 miles, if you think back to that example, how much of the variability of my prediction line is blamed on just the equation of the line itself? Because we know that the equation of the line is not going to be perfect. We know that the equation of the line is going to be off a little bit. It's not ever going to be a perfect model. It's very rare to get a perfect model for your data set. So how much of that variability, how much of that residual can be blamed on the LSRL? Okay, that's what R squared is. R squared tells us how much better the LSRL does at predicting values of Y than simply guessing the mean of Y for each value in the data set, okay? So we don't want to just guess the mean Y. We want to look at how much of the variability is blamed on that line and how good of a model that line is, okay? If your R squared is closer to 1, like if it's a 99% or something, that's going to be a really good model. You want a high R squared to say that your variability can be blamed on the line, because then it's not blamed on other things. It's not blamed on other variables. It's not blamed, there's not a lot of other factors that are playing into that, okay? So having a high percentage for your R squared is a good thing. This is a really hard concept. I have linked a second video. It's not a requirement. You don't have to watch it, but there is a video inside this assignment. It's from this guy who's been teaching AP Stats for a really, really long time. He calls himself the AP Stats guy. He has a YouTube channel and he does videos on a whole on every topic basically, and he just has a really great way of explaining things too. So he talks about R and R squared in his video, and I linked that video in our assignment on Schoology. So feel free to check that out if you just want to hear a little bit more about what R squared is, because it's kind of a confusing thing. But if you can remember the fact that it's literally the square of R, and you remember that R is between -1 and 1, then you can kind of lead yourself to the fact that, oh yeah, R is that percent. Oh yeah, it's the percent of variability that I can blame on the line. I can blame a certain amount of variability on the line, so then that's my R squared. All right, so let's talk about interpreting things. So we're going to go back to that Ford F-150 example again. It says, recall that for a random sample of 16 used Ford F-150s, the least squares regression line was equal to P hat, price hat, equals $38,257 minus 0.1629 times the miles driven. For this model, technology gives an S value, or in other words, a standard deviation of $5,740, and it gives us an R squared of 0.66, okay? So if we interpret these two things, part A was interpret the value of S, because it's not always about just finding the value of S. Our calculator is going to find the value of S for us. We're not going to do that by hand. I know they had to put a big formula listed out for you a couple slides back. I didn't even talk about the formula because you're not going to do it by hand. You're going to do it on your calculator, and that's fine. This is the piece that's going to be important, okay? Being able to interpret that. So what that S value means, it says the actual price of a Ford F-150 is typically about $5,740 away from the price predicted by the LSRL, and you always, always, always have to state with X equaling miles driven. You always have to put the X variable in. So you're talking about the dollar amount, that's your Y variable. You put context by talking about the example or talking about the whatever the problem is finding. So your data set is on the Ford F-150s. You label your values with dollar signs. That's great. You talk about the difference between the actual price and the predicted price with the LSRL, and then list out that X value. Okay, I like this as a template. If you're a person who likes to have a template when you're asked to do things like interpret the S of the residuals, what does this mean? There's your template for writing out that interpretation. Now let's talk about R. So for R squared, let's talk about R squared. So for R squared, we found an R squared value of 0.66. Now remember that that's a percentage, so we can say about 66% of the variability in the price of the Ford F-150 is accounted for by the LSRL. That you're going to see, those words right there, is accounted for by the LSRL, or the least squares regression line. That is going to be in every single statement regardless of the context. If you're ever interpreting R squared, that little phrase right there, that's in there. Boom. And then with whatever the X variable is. So 66% of the variability in the price of the Ford F-150 is accounted for by the LSRL, with X equaling the miles driven. That's how I would write up those two interpretations. So here's just one more thing to kind of think on. It says both S and R squared are calculated from the sum of the squared residuals. The sum of the squared residuals. That's where we get those two values. They also both measure how well the line fits the data. The standard deviation of the residuals reports the size of the typical prediction error in the same units. That's an important thing to note. The standard deviation has units. R squared is a percentage. It doesn't have units. So for example, in the truck example, you got an S value of 5,740. That label was dollars because you're in the same units of it's the typical amount of distance in the Y, and the Y was measuring dollars. Okay, then it says the value of R squared, however, does not have units, and it's typically expressed as a percentage. So such as R squared was 66%. Because these values assess how well the line fits in different ways, we recommend that you follow the example of the most statistical software and report both. When you do your one variable statistics on a LinReg, you're going to get both of those values. You're going to get R and R squared, and you're also going to get your S value for the residuals. Okay, you're going to want to calculate both of those things. That's basically what they're getting at here. All right, so that is our very brief discussion on S and R squared. Again, R squared is kind of, S you can kind of wrap your head around because it's like, oh yeah, how off is my line? What's the typical distance that my actual data is away from the prediction line? That makes sense in our heads. The R squared thing is a little bit trickier to wrap your head around. So I really encourage you to look at that other video. And don't forget, there's also those AP stats videos from College Board, from my AP. So you can watch the My AP videos as well, and they will talk you through it in a different way than I will. So sometimes it's just nice to hear other people talk about the same thing, and then it'll click a little bit better. So anyways, thanks for listening, and I will catch you next time.